The fundamental theorem of calculus, special case on the interval a to b, where delta x is b minus a over n. And we'll explain all this a little later. Remember my video of finding the area under the curve. If you haven't seen that video, go watch it. Just do a search on YouTube for Murdick and calculus. Just Murdick and calculus, those two words, and then all the calculus videos will pop up. Watch the finding the area under the curve video, and I think you'll get a lot more out of this video. Okay. We used the sum of products in that video, and we used what they call the right side of the triangle for the height. That might not mean anything to you if you haven't seen the video, so definitely watch it. But if you have seen it and enjoyed it, I hope, what we did was we found the area under the curve y equals x squared from 1 to 3. Okay, and we used these rectangles to do it, the area of these rectangles to do it. We got the base of the rectangles by partitioning the x-axis into 4 parts using that delta x formula, b minus a over n, in this case 3 minus 1 over 4. And we got the heights of the rectangles by plugging in a function of x1, or 1.5 squared, that gave the height of the first rectangle, and 2 squared gave the height of the second, etc. And that's what I said. Remember, go back and watch it a little bit. And when we did that, we got a sum of products, okay? And I copied this right from the other video. And here's the formula, sort of the formula we use, function of x1 times delta x. That gave us the area of the first rectangle. Here's the area of the second, etc. And then we actually calculated it here. And we got an area of 10.75 in that problem. And we overestimated. We know that it's less than that, but it's an approximation. We can generalize this big formula here. And that's what I write next. We can generalize this formula for as many rectangles as we like, all the way up to n rectangles. And the more rectangles you have, the less error you have. And if you have like 1,000,000 rectangles, then there's hardly any error at all. And we can generalize, we can actually make this long formula here more concise by using sigma notation. If you're not familiar with sigma notation, I would get familiar with it. I'll probably make a little video on sigma notation because I usually teach it to my calculus students, so you might look for it. But anyway, here's the more general formula for n rectangles. Okay, this is for n rectangles, and the definite integral can be defined in this way. If we take the general formula for n rectangles and take the limit as the number of rectangles that you use goes to infinity, that's a lot, right? Millions and millions of rectangles divide little teeny, with very small bases, because as n goes to infinity, of course, delta x gets very, very small. And if we take it and generalize it in this way as a limit, we can say this equals what we call the definite integral. Notice the sum sign is changed here a little bit, and from a to b, and this equals big F of b minus big F of a. Kind of neat, huh? Where big F is the antiderivative of little f. And the way I define that is I say, okay, where the derivative of big F is little f, meaning that big F is the antiderivative of little f. Let's go back to our example from the video of finding the area under the curve, only this time we're going to find the exact area. Find the area under the curve of f of x equals x squared and the y-axis. In other words, this wedge-shaped object here. This is the y-axis here. I'm sorry, the x-axis, what I should say, shouldn't I? I mean, I should change that to x. There we go. And the x-axis, okay, it's y equals 0, but it's the x-axis. So it's this wedge-shaped object here. We're going to find that from x equals 1 to 3. And the last time, remember, we got 10.75. But this time we're going to use the definite integral. The area equals the definite integral from 1 to 3, which is big F of 3 minus big F of 1, where big F is the antiderivative of x squared. Now we know the antiderivative of x squared is x cubed over 3. So we're going to evaluate it at 3, and then we're going to subtract the same thing evaluated at 1. So if I evaluate at 3, of course, I'll get 27 over 3 minus 1/3, which is 26/3, which is approximately 8.67 square units, whatever the units are. And last time we got 10.75, so this is less, right? And this is the exact, actually 26 thirds is the exact area under that curve.